Want to see how to build code-first Azure ML models? Come with me, let's write some code. Welcome to this video on Azure Machine Learning. My name is Kevin Fiesel. I'm the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. We've spent a few videos building up to this, and in this video, we are going to train a code-first Azure ML model. We've set the stage. Let's jump straight to the code. We are in Visual Studio Code, looking at the pipeline folder, and there are quite a few scripts. Before we jump into the code, let me give you a brief overview of how I've laid out this code. We have two relevant folders, config and scripts. The config folder holds a series of YAML files describing the functionality we need, and the scripts folder holds the actual Python scripts. We'll see what these files look like in a moment, but let me now open up the deploy-train.py script. This is a Python script I've written to train a model on the Chicago parking tickets dataset, specifically covering whether we believe a person will pay their ticket or not. I have a series of import statements taking up the first 22 lines of code, but the only thing I want to point out is that the block from 11 to 22, where we bring in the azure.ai.ml namespace. This is the Azure ML SDK v2. If you're looking at Azure ML code which doesn't use azure.ai.ml, you're probably looking at v1 code. The SDK v1 is still around, but the primary avenue for new development is v2, so that's all I'm going to care about in this series. The next big block of code covers some Azure ML setup ceremony, like specifying my workspace name, specifying the compute cluster I'll use, and loading up the workspace. I also have a block in here from lines 38 to 70, which ensures that I have a valid compute cluster available. If Azure ML can't find the compute cluster, it will create one for me based on the specification I have here. This can take a while if you don't have the cluster available already, but it is a one-time cost. Moving down to line 72, I begin the process of defining pipeline components, starting with a specification that the parent directory for all of my configuration files is /config under the local path. The dot is there because otherwise Azure ML would look for a folder at the root of my file system called config, and that's not where my code actually is. Lines 77 to 82 cover the process of loading components using a built-in Azure ML function. We can see that I load each YAML file one at a time, and what I get back is a function. For example, I create the function replace missing values on line 77, and we can use it on line 86. Let's now dig into these functions to see how they work, as I don't want there to be any magic here. I'm going to open the feature replace missing values.yml file. This is a YAML file including an Azure ML specification. We have a component name, which includes underscores, and a display name, which is what will show up in the Azure ML user interface if I view the execution graph for this training pipeline. I've specified that this is version 1 of the component and that it is a command. Then I specify inputs and outputs. I have one input, a folder called input_data. I also have one output, a folder called output_data. The code itself will be in the scripts directory. Because our current context is in the config directory, I need to move up one level and then into the script to find the Python files. The next line specifies the environment I'll use. In this case, I'm not doing anything special, so I'll use a built-in Azure ML environment, one which includes the Lite GBM trainer. This environment is using fairly new versions of libraries like scikit-learn, and it already includes everything I need for training, so I won't need to specify my own here. Finally, we have the command. Note that command scripts always start with that angle bracket and hyphen. Then, we want to run the Python executable and kick off a script called feature_replace_missing_values.py sending in our input and output data variables. Given that YAML specification, we can now move into the script itself and see what's happening here. This script is fairly short, only about 50 lines long, and most of it is boilerplate. Lines 13 to 17 cover argument parsing, which is a way we can ensure that callers send in all the parameters we need for a call, and that those parameters are in the correct format. In this case, note that the URI folder parameters get converted to strings in Python. We're going to run this code on our own compute cluster and in a Docker container based on the environment we specified, and that container won't have the SDK installed. Lines 19 through 29 are diagnostic in nature and intended to tell a person debugging the script where they're at in the process, as well as the contents of the input data folder. Then, lines 31 to 36 will loop through each file in the input data folder. For each file, we'll create a new input data frame and then append that data frame to a list. Finally, line 39 will concatenate all of these together. That way, we could have dozens of training files in our input data folder, and we'll get all of the data from all of those files. Now we get to the actual meat of this file, which is just lines 41 to 44. We are replacing missing values of police districts. Basically, if the police district is missing, we'll replace that nan or none with a 0. The reason we are doing this is that some algorithms don't like nan or none, and will fail if you have any missing data. I could probably dig in deeper and figure out which police district each row belongs to, but for the purposes of a simple demonstration, I simply filled them out with zeros. Finally, line 48 writes the results to a new CSV file in the output data folder called replacedmissingfeatures.csv. Note the index equals false on this line. The reason I do this is that I don't want pandas to omit an extra column with the row number. So that was the first script. If we go back to deploy train.py, we can see that there are several of these scripts here. I won't dig into each one individually. You can grab the code yourself and try it out if you'd like. But I will note two things. First, if this were a real ML pipeline, I would probably combine the scripts for lines 77 through 80 together into a single preprocessing script. The reason I split them out was to show that you can have pipelines of any arbitrary length. So I think it was more illustrative to go a bit overboard. The other thing I want to mention is the final pair of scripts, train model and register model. This is where things start to get interesting in our pipeline. Before I get too far into those, let's keep going through this deployment code. Line 84 begins our first real function called build pipeline, which takes one input called raw data. This has a tagged attribute called pipeline and lets Azure ML know that this is our main pipeline function. In it, we put together the pipeline components we just loaded. The first function call, replace missing values, takes in our raw data as input. But note that the second function call, feature engineering, doesn't use raw data. Instead, it uses the output of the prior step as its input. We see the same thing for feature selection and then split data, showing that we are chaining together each of these operations, one after the other, in a specific way. The next function call, train model, looks quite a bit different. It starts out with two inputs, train data and test data, both of which we get from the split data function. If I open up that split data Python file and scroll down a little bit, we can see that the meat of the file happens on line 47. On that line, I call train test split from sklearn.model_selection. I'm asking for two output data frames, one that I'll call train df and the other test df. The test data frame will contain 20% of my data. Let me briefly give you my reasoning for 20%. Oftentimes, when people ask, how much data do I need to hold back for testing? The answer you'll hear is something like 30%. The idea is we want to have as much data go into our training function as possible. That way, our trainer can get the clearest picture of our situation as it can. But we also need to reserve enough data that our test data set reflects reality as best as it possibly can. Well, this leads to a challenging trade-off, as we can only use data in test or in train, but not both. But in both cases, we want as much data as possible. So how do we square this circle? The answer is that we weigh our training needs more heavily than our testing needs. So we almost always take the majority of our data for training. The rule of thumb here is approximately 70% for training and 30% for test, if you don't have any information to change that calculation. In this case, I have 1,000,000 data points, and I'm reasonably confident that 200,000 unseen data points is plenty for testing our model. For that reason, I chose 20% for test, so that I could gain an additional 100,000 data points for training compared to that rule of thumb. I might even be willing to shrink the test percentage further, but I figured this was a reasonably safe compromise between maximizing training data and maintaining enough for testing to work. With that aside out of the way, the last parameter is a random state, which I fixed at an arbitrary number. That way, the data is fairly stable between runs, so I can demo this repeatedly and get similar results. That's our split data function. Now let's jump into the train model script. This one looks a bit different from the others. We can already see that the imports section is longer. Also, because I have so many arguments to parse, I decided to create a main function and perform argument parsing down near the bottom. If I scroll down to line 152, I have the definition for parse args, specifying each of the required input parameters and types. Then on line 168, I kick off the job. First, I start a run with MLflow. As we learned in the prior video, we're really kicking off an Azure ML run, but our code doesn't need to know this. Then we parse arguments and call the main function if everything is fine. After we complete the main function, we have a call to end our run. Now let's go back up to line 28 and the main function. Inside here, we pull in each file in the train data folder and then each file in the test data folder, making sure that we keep those separated. This creates two data frames, train df and test df. Then on lines 53 and 54, we call a function called process data, once for training and once for testing. The process data function begins on line 76 and it breaks out data. We have three subsets of data: numerical data, categorical data, and our label column. What we're doing here is fairly straightforward. First, we take everything but the label column and specify that as X. Then we take the label itself and specify it as Y. After that, for each categorical variable in X, we'll specify its type as category rather than string. That way, we can let scikit-learn know that this is categorical data. Each numeric type will be a float for the sake of simplicity. Then we return the split data. Now, if I move back up to line 57, we have a series of hyperparameters that are common for gradient-boosted decision trees, which is the class of algorithm I've chosen for this demo. Gradient-boosted decision trees, especially using a library like XGBoost, tend to perform very well for classification problems. And way back when we performed automated machine learning in Azure ML, we found that LightGBM, another gradient boosting library, did a nice job of solving our problem. The only thing I'll mention about these hyperparameters is that we're passing most of them into this function call, save for validation fraction and random state. The validation fraction covers how much of the training data we'll use for hyperparameter tuning, 10%. The random state, once again, is something that I've fixed to allow this to be a bit more repeatable. Now that we've split the data and put together our hyperparameters, I can call the train model function, which I do on line 67. This jumps us down to line 103 in the code. Lines 106 through 109 handle transforming the categorical data into something that gradient-boosted decision trees can understand: numbers. With this algorithm, everything needs to be numeric. So the way we're going to convert these strings to numbers is using a technique called one-hot encoding. To visualize this, we can pivot each variable into a set of columns, and the value for that column is 1 if there's a match and 0 otherwise. It's a simple technique, but it works really well in practice. Lines 110 through 113 work on our numeric features. First, we replace any missing data with the median. There are a few rows with missing inputs for things other than police district, so here's where we'll handle that. Then, we scale all of the values to fit between 0 and 1, a process called normalization in the ML world, but totally different from normalization in the database world, so don't get those concepts confused. The reason we want to normalize our numeric data is that some algorithms are sensitive to major differences in scale. Like if you have values ranging from 0 to 1 in one column and 0 to a million in another column, the algorithm might incorrectly prioritize changes in the column with larger values simply because there's a bigger range to work with. To avoid this, we rescale everything to fit within a given range, which canonically is 0 to 1. Line 116 defines our gradient boosting classifier, sending in the hyperparameters we'll use. Then, I call the scikit-learn make_pipeline function for our classifier, sending in how we'll transform each column. After that, on line 118, we train the model. Then, on line 120, we generate predictions based on our test data, and lines 122 through 128 give us a series of calculations to tell us how we did. We store these results in a dictionary, print them out to the console, and also log them in MLflow, or rather the Azure ML pipeline run. Finally, we return the model and results. Now scrolling back up to line 70, we use MLflow to save our model to the output location, specifying a signature that I can use for consuming the model. Finally, we write the evaluation results out to a JSON file and end training. Jumping back to deploy-train.py, this takes us through line 97. On line 98, we register our model using the model output and the test report. Let's quickly jump into register_model.py and see what it does. On line 12, we start an MLflow run. Then, starting on line 28, we get the context of our current run and workspace. On line 32, we load the model that we just finished training, as well as the results file on lines 35 through 37. After that, lines 40 to 42 save our model to a local file path. Lines 45 to 52 take that locally saved model and register it with the Azure ML model registry, calling the model Chicago Parking Tickets Code first and providing a description for that model. We take the results and save them as tags, so that way we can easily see how well the model performed. And on line 54, we end the run. Now that we've seen how the registration function works, let's go back to deploy train one more time. Our build pipeline function needs to return results from the pipeline, so I am emitting the model and report from model training. The next function is on line 102, where we prepare the pipeline job, running it against a cluster. This is where we tie everything together. First, we need the dataset for training, the Chicago Parking Tickets folder dataset in Azure ML. This is of type URI_folder, and the input we generate we'll call raw data on line 105. On line 106, we create a pipeline job based on the build pipeline function. After that, I have a few parameters I'm setting, including the cluster name, default data store, display name, and that I want to force rerunning. Typically, you don't want to force rerunning because it's a waste of computational resources. But because this is a demo, I want to make sure each time that I run it anew. Finally, line 115 calls our prepare pipeline job function, passing in the cluster name that we defined earlier. Line 116 actually executes the job. So up to this point, we've just been loading files locally and telling Azure ML what it should do. But this is where things get serious. I can execute this job by running a simple Python script. Python space deploy hyphen train.py. Running this will take a bit of time, unfortunately, but you don't have to experience this pain. Let's just cut right to the end. I'll pick it back up when the job completes. Okay, now our pipeline job is complete and it ran successfully. If I return to the Azure ML UI, I can navigate to Jobs and choose the Chicago Parking Tickets Code First experiment. We can see a few pipeline runs, so let's look at the latest. Selecting it, I can get a visualization of the pipeline graph that we created in text. That's pretty neat. Also, if I select the Job Overview button, I can navigate to Metrics and see the outcomes. Our accuracy was somewhere around 76%, which is pretty good. This model does suffer from some of the recall problems that our AutoML models had, so that's not too surprising. But all in all, this model performs pretty well, and actually a little bit better than what we got with automated machine learning. Speaking of models, let's navigate to the Models tab and choose the Chicago Parking Tickets Code First model. We can see that the latest version is version 2, and we also have our results listed as tags. There you have it. We ran through a lot of code in this video, but the upshot is that we were able to get a model trained and registered in the Azure ML model registry. In the next video, we are going to execute a process to perform batch scoring on another data set using that newly registered model. We'll have links and show notes in the description below. And until we see each other in the next video, take care.